One of the largest scale atmospheric circulations that we deal with on a daily basis would be the jet stream. Now, jet stream is just a very fast channel of wind. By fast, we're talking about 100 to 200 knots. And you can see that it occurs about 10 to 15 kilometers in altitude, thousands of kilometers long, even all around the whole world sometimes. It can be several hundred kilometers wide and a few kilometers thick. We're going to talk about the polar and subtropical jet streams, and there are more jet streams than that. When we usually talk about the jet stream, we're usually talking about the polar jet stream. Okay, I figured before we go on any further, let's see if we can actually identify the jet stream today. So here's a really cool website where all the global winds are indicated by these animations on the surface of the globe. You can see here is North America. So we're looking at the northern hemisphere right here. What we see is a very fast channel of air following along this direction here. You can see it's especially fast right here, and then it gets quite fast again down here. So here we have the polar jet stream, very fast here, and somewhat fast here. Notice how the jet stream dips down. Remember that the jet stream is going to follow the your 500 millibar altitude lines. And so your 500 millibar altitude lines are going to follow the same pattern. Let me just show you that figure as well. Here's the current 500 millibar chart. Sure enough, it dips down, the jet stream dips down with the 500 millibar contours, which means we have a trough over the western US right now. So you can see the trough there with the jet stream right here. Now, this is a global jet stream, so we're looking at the North Pole. Let me zoom out a little bit so that you can see. Start off here. Here's our jet stream. It comes around, drops down into that trough we just identified, comes back along, and then picks up into a really strong current as you get above Great Britain and Scandinavia. Then kind of weakens out a little bit and then gets stronger again as you come around through Russia and China. And then as you go across the Pacific Ocean, you've got a big trough there. It comes back into the western hemisphere over Alaska right here. So you can see this is a global scale wind circulation. So what causes a jet stream? A jet stream is established when you have steep temperature and pressure gradients between circulation cells. So we talked about the Hadley cell, which is the cell that goes between the equator and 30 degrees latitude, the Ferrel cell, which goes between 30 and 60, and the polar cell, which goes between 60 and the pole. Okay. Between each of the two cells, there's going to be a slight difference in temperature and most definitely a difference in pressure. Now, there is a slight temperature and pressure gradient between the Hadley and Ferrel cells, so you're going to get a decent current here. And then because the Coriolis force that turns that current to go this west to east over the convergence of those two cells. However, the gradient between the Ferrel and polar cells is much stronger. And so you end up with a much stronger jet stream over 60 degrees north and 60 degrees south latitudes. This is why when we talk about the jet stream, we're talking about the polar jet, because that is the stronger of the two primary jet streams. Okay, again, this is an atmospheric circulation that is global in nature, goes all around the whole world. But it's not necessarily consistent. As we saw here, coming back here, here was your jet stream coming over Europe, but then over Eastern Europe, it kind of died out a little bit. It wasn't very strong. Likewise here, came across the United States, and then it kind of died out over the Atlantic. jet streams are not always consistently strong all the way around the globe. Sometimes, like we have in this figure, you have a jet stream that comes along and then it weakens and dies out and then picks up again a little bit later on. But what's cool is that we showed in this figure here on the left, as well as the wind diagram that I showed you here, we can see data that indicate the jet stream. But we can actually look at satellite images and see that jet stream. So here is a satellite image that corresponds with the figure on the left. And these, you can easily see the jet stream by following the cloud patterns. Also notice there is another strong current of air in the southern U.S. This is our subtropical jet, which sure enough we see coming across Florida. There are lots of other jet streams. There is the tropical easterly jet stream, which would be a jet stream over the convergence of the two Hadley cells. In other words, it's right on top of the ITCZ. You also have the low-level jet, which is a nocturnal jet. That's a jet stream that forms because of the difference in temperature and pressure between the daylight side of the Earth and the nighttime side of the Earth. You also have a polar night jet stream, which is a jet stream that forms over the poles during their winter. Remember that the poles during their winter experience 6 months of night. And so since it's night for 6 months, you generate some very strong currents in the polar regions. Okay, so that's atmospheric jet streams or atmospheric currents. What do they have to do with ocean currents? Believe it or not, ocean currents are very related to atmospheric currents. In fact, ocean currents are a result of atmospheric currents. Ocean currents are formed as the ocean is dragged by wind. When you have a cold current, that's because you've got ocean being dragged from the north, colder north polar areas towards the south. And we usually see these on the west side of the continents. You also have warm currents coming from the warmer south towards the colder north, and usually that happens on the eastern side of continents. We'll see that in just a second. All right, here is a chart that shows the basic ocean currents around the world. Now let me show you exactly what I mean by these currents are dragged by atmospheric circulations. Remember that the easterlies happen near the equator between 0 degrees latitude and 30 degrees latitude. So those are the northeast trade winds, come from the northeast, drag the current along with it. And then between 30 and 60 degrees latitude, you have the westerlies, winds coming from the west to the east, dragging the water along with it. And then from 60 degrees to the pole, you have easterlies again, dragging that water in that direction. And so we create ourselves a circulation that goes in this direction, going to the west because of the northeast trade winds, and then to the east again because of the westerlies. And of course you have a mirror image of that in the southern hemisphere for the same reason. Now here's, remember in the last slide we talked about cold currents on the west side of the continents. Here's why. You have this warm current being pushed towards the north, and then it picks up cold water and pulls that cold water down along the western coast. But on the eastern coast, you have the warm water from the equator that's being pulled up towards the coastline in this direction. And that's a good summary of both atmospheric and oceanic currents.